There are 8 million YouTube talks online, but if you want to really experience it, you have to come in person. It's great. I mean, you'll just meet such cool people.
Okay, so welcome everyone. I'm Gabor and I will talk about static analysis. I will mainly talk about how static analysis works, how is it implemented. If you are more interested in how to use it and what features do we have to offer, I would recommend checking out Sunny's talk. It was earlier this week. Hopefully the recordings will be up soon. So welcome everyone to this year's CppCon, and in case you are interested in chatting about some of the products we are working on, I encourage you to join to our Discord channel. And even if you are not using any of the products we are working on, feel free to take the survey because this will help us improve them and make them ready for your use cases. So today, first I will talk about what path-sensitive static analysis is, what kind of checks do we have in MSVC, and a look under the hood, what makes this sort of analysis work. I will also briefly discuss some of the features we are working on and summarize the lessons learned. So I wanted to give a short glimpse into my journey to this point. So I started working with compilers in 2012 and participated in Google Summer of Code first as a student, and liked it so much that I am participating as a mentor ever since. And in 2015, I was interning in Apple's compiler team and started a PhD in this topic later. I briefly did some big data stuff, but quickly realized compilers are where my passion is, and got an internship at Microsoft, where I was lucky enough to work with Herb Sutter to implement the lifetime analysis that he was working on. I continued this work the next year, and then I worked in Google's Fuchsia team, and later on joined Microsoft full-time and finished my PhD. So first, let's talk about static analysis. When I talk about static analysis, I mainly mean tools that can find bugs in the source code. So we have a tool and we feed source code into this tool, and this tool uncovers potential bugs. And the reason why it is useful to have such tools, because testing is not always sufficient. For example, in this code snippet, there is a division by zero error, and if I were to do random testing, there is a relatively small chance to pick the right value that would trigger this bug. On the other hand, using static analysis, I can do a systematic approach that can find this error. On the other hand, while we can rely on engineers writing tests, C++ is a complicated language and programming is a complicated discipline. So basically, it is easy to miss out important cases. So static analysis is a good supplement to all of the other methods we have to improve the code quality. There are three main categories of analysis. One is the flow insensitive analysis, that is type checking. For example, it is an error to assign a string to an integer variable, and it is an error regardless what is happening before or after that statement. So it is not sensitive to how the code execution flows. There are the flow sensitive checks that I will introduce in a moment, and the path sensitive checks that I will introduce after that. So instead of discussing the general abstract idea, I like to give you examples. And in this case, there is a code snippet, and I would like to find potential null dereference errors in this code snippet. So when I'm doing flow sensitive analysis, initially, when I start to analyze this function, I have no idea what p is. Is it a null pointer? Is it a valid pointer? I don't know, because maybe it is in the contract of this function that it needs to be called with a non-null pointer, and in that case, this value will never be null. But just by looking at the function, I cannot know, and this is why I have this unknown value. And I start to evaluate the function, and there is a branch, and in that branch, there is a condition, and because of that condition, I know that within that branch, the value of p cannot be null. And if I do not take the branch, then basically in flow-sensitive analysis, I always want to have a single state representing all of the possible runtime states at that point in the analysis. So I need to merge the information coming from the branch and jumping or skipping the branch. And in one of the cases, the value of p was unknown, and in the other cases, the value of p was not null. And there is a structure called lattice that tells us how to merge these states. So in this case, merging not null and unknown, the result is unknown. And this is basically a safe approximation of the runtime values at this point. And in the next branch, we see an assignment. So the value of p is null. And after, when we merge the states from the branch and skipping the branch, the value will be maybe null, because there was a path where the value of the pointer was null. And when we take the final branch, we will see that the value of p is maybe null, and we are dereferencing this pointer, so we will emit a warning. The problem is with this approach, if we look at the code more closely, the variable var is only set to 1 when the value of p was not null, and we only take this branch when the value of this variable is 1. So basically, this error can never happen at runtime. We gave a false warning. So to summarize what we learned, question?
What's the difference between unknown and maybe null?
Yeah, so that's a pretty good question. So so the question was, what is the difference between unknown and maybe null? And the difference is that in case of maybe null, we had some evidence in the code that null is a possible value, because we did see that there was at least some path where null could flow into this program point. And in case of unknown, it is still possible that the null could flow into this location, but it would flow from outside of the function. So when we only emit warnings for maybe nulls, but not for unknowns, we can emit higher confidence values compared to when we would also emit warnings when we reference unknowns. Okay, so to summarize some of the key points from the previous slides, not all of the possible paths can be realized at runtime. For example, it is not possible not to take the first branch, but take the third branch in this code snippet. And any warnings that we would find on these invisible paths, those would be false positives, noise for the users. And in order to figure out what paths are invisible, we need to reason about the whole of the program state, not only about pointers, but all the other variables. So these are some of the shortcomings of flow-sensitive analysis. It is hard to deal with this invisible path problem. So I want to emphasize that flow-sensitive analysis is still useful, but it has a set of problems where it is a right fit. For example, Rust's borrow checker is a flow-sensitive analysis. If you want to learn more about flow-sensitive analysis, these are the two resources I would like to recommend. The first one is a lecture notes that is very well maintained, and it is a good resource for someone who is more mathematically inclined. And the second one is more geared towards implementations and engineering. So let's look at path-sensitive analysis, and let's look at how path-sensitive analysis can help with the previous problem. Specifically, how can we avoid false positives like the one we had before? So we will look at the same code snippet that we were analyzing before, but we will use a slightly different method. So in this case, in the analysis state, I will record everything about the program that I can. So I know nothing initially about the value of p and the value of cond, and I know that var is initialized to 0. So for the two values that I know nothing about, I will introduce unknown symbols. So these (1) and (2), these are two symbols that can have any value, and at this point, I don't know anything about these values. So when I start to execute this program, or start to analyze this program, then when I take the first branch, because of the branch condition, I know that the (1) value cannot be null. So I can record this constraint in the program state. And there is an implicit else branch, and if we take the implicit else branch, then the value of p must be null, otherwise we have taken the branch. And the trick is in path-sensitive analysis is that we do not merge the states. So in this case, after taking both the branch and the implicit else branch, we keep those two states separate, but we recorded the history and all the information we know on each of the paths into those analysis states. And when we visit the second branch, we have two states to work with. So we want to know whether we can enter this branch from any of those states. And in this case, we know nothing about the value of cond. So from both of these states, we can enter this branch. And after we enter this branch, the value of the pointer is set to null, and the value of the variable is set to 2. But we can also skip this branch, take the implicit else branch, and in this case, the value of the pointer and the value of the variable did not change, and we know that the value of cond is 0. And this is the interesting point. At this point, we have 4 separate states, and we have a condition var equals 1. So basically, we can only enter this branch if this condition is true. So we can look at each of the states and check which of the states can meet these conditions. So in this case, there is only one state where we can enter this branch, and in this state, the value of the pointer is guaranteed to be not null. So basically, this was the tricky part of the path-sensitive analysis. We have to figure out which of the states can reach certain program points. So before moving on, I want to give you the anatomy of a path-sensitive analysis. What are the names of the stuff that I had on the screen? So we have program states that are representations of the runtime states, but during the analysis. And we have transitions between these states. But we don't only, so in order to describe a program state, we also need a program point, because the program might have the same analysis state in multiple points. So we have the transitions between the program states, and in a program state we have 2 components. One is the store or bindings, that basically is a mapping between the entities in the source code and the values that we are reasoning about. And we have the path condition that accumulates all the information that we know about the unknown values. And whenever we reach a condition, we try to use all this knowledge, the knowledge we have in the store and bindings, and the knowledge we have as constraints, and we make a query to a solver, and the solver will try to determine whether we can take this branch or not. So doing this path-sensitive analysis is useful because we can get rid of many false positives, because we have a way to deal with the invisible path problem, at least it's in certain cases, but there is a huge performance penalty. So there is a trade-off between performance and precision. So maybe you noticed the number of pads can explode because it is exponential in the number of the branching factor. And if you think about a service that can potentially run for a really long time, potentially forever, it has a loop inside, there are an unbounded number of pads because we could exit the loop in the first iteration or the second iteration and so on until infinity. So we have no computation resources to check all of the execution pads. We usually check a subset of the pads. And we try to select an interesting subset of the pads to reach as many errors as possible. And there are certain optimizations that can make this sort of analysis faster. There are 2 papers on this slide. So those are links. The slides will be available. And those papers are describing some methods. How can we reduce the number of states that we need to explore by merging certain states? So MSVC has multiple checks in both the path-sensitive and flow-sensitive categories. Each of these links will lead to a blog post where you can read about the details of these checks and also how you can enable them and try them out. And we're also planning to ship more checks in the future. So during the rest of the talk, I will talk about how can we represent the store in more detail. And I will also tell you how can we evaluate those conditions that are a crucial part of path-sensitive analysis. And at the end, I want to give you some tricks. If you see a false positive result from a path-sensitive analysis, how can you deal with that? And how can you make your code easier to understand in the process? There are many details that we will not have time to look into. For example, the data structures that we use to implement this analysis, and also how we deal with certain code constructs like loops. Hopefully, I will be able to cover those in some future talks. So let's look at one of the first challenges. When we want to reason about the code, we have a very good tool for reasoning. It's called math. The problem is, with math, we can reason about values. And in the source code, we have way more complicated constructs like arrays and pointers and aliasing. So one part of the challenge is how can we map the constructs we have in the source code into pure values that we can reason about. And this slide is an attempt to explain that. One way to do that is to build a graph that is modeling the layout of the memory. And in this graph, the edges are the includes relationship. So, for example, if I look at the code if I look at the program point that is highlighted on the screen, we have an array, and in that array we have elements, and in those elements are structs, and those structs have members. So a member is included in a struct that is an element of the array, and that array is on the stack. So here we can represent this with this graph. And we have 2 elements, and those 2 elements are aliased because there is an assignment in the code where we assign one pointer to the other. So if we represent also the memory that is the pointee of those pointers, then we have the store as a data structure that maps memory locations to values. The interesting part of this mapping from memory locations to values is that memory locations themselves can be values because the value of a pointer is a memory location. So in this case, both the P of the element with the index 1 and the P for the element with the index 3 points to the same object, and that object has the value 5. So here the dashed arrows are representing the store, and the dashed arrows represents the mapping from memory locations to values. And this is called the graphical approach because we have a graph representation of the memory, and this representation is used by the Clang static analyzer. On the other hand, there is an alternative approach. In the alternative approach, we are not materializing the graph that represents the memory, but we basically record which set of names refer to the same object. So in this case, A1.p and A3.p will mean the same value. So we can use a set to describe this, and we can use a representative of the set. So every time we name a value, we want to have a unique name for that value, so we can use the representative of this set. We call this representative the alias master, and in this case, the store is a map from the alias masters to the values. And one of the interesting points of this representation is that we no longer need to have memory regions as values, because when we have a prefix of the path is already a name, and that name basically has the identity that we need. So when we have the a sub 1.p without the reference, we know that that's already a memory location, and we don't need to represent that in any sort of graph representation. So this is just a lightning whirlwind introduction to access paths, because this approach is called access paths, and this is what we use in MSVC. If you want to learn more about that, I would recommend you to look at this lecture. Okay, so now that we have a way to map source code entities or names in the source code into values, we need a way to reason about these values. And usually when we execute the source code, we have certain states at runtime that we can reach, and we have certain states that we cannot. For example, if we have a program with two variables, x and y, we might have a state when the value of x is 15 and the value of y is 10, but we might not have we might not be able to reach a state when the value of x is 15, but the value of y is 11. So it would be nice to precisely track what are the combinations of values that the program can reach. Unfortunately, it would be really hard to collect all of those constraints, and it would be really memory intensive and computationally intensive to reason with information that is this precise. So we often use approximations. So when we are not sure what are the exact value pairs that might appear in the program, we might be able to give some bounds. For example, we know that x is between 10 and 20, and y is between 10 and 30. And this way we can describe a program state, and we can use this program state to evaluate certain conditions. We have also more sophisticated models. So if we use octagonals, we can also compare variables to each other. So we can express things like x must be less than y. And we can go even further. We could use Polyhedra to represent the states. In this case, we can have arbitrary linear expressions to describe the constraints that we have. And we use a Polyhedra model in MSVC's static analysis tools to reason about the values. And I wanted to show you how we can use such a model to reason about the source code. So in this case, I would like to show you, using an example, how can we prove a certain indexing operation correct. So let's imagine we want to prove this indexing correct, and let's see what can we do about it when we are using static analysis in a flow-sensitive manner. So First, in order to reach to the program point we are interested in, we have to skip the first branch. And if we skip the first branch, we know that the value of x must be smaller or equal to than y. We also need to skip the second branch, and because of that, we can record the constraint that x is non-negative. And we also need to skip the third branch, and in this case, we can record the constraint that y plus x needs to be smaller or equal to 9. And when we reach the statement where we index into this array, we have a precondition to this operation, and this precondition is based on the size of the array. So all of the valid indices is between 0 and 9. So using all this information, basically what we want to know, given the facts we collected before, is the precondition of this operation always true? And one way to express this using a query, we can use a system of inequalities. So basically, we can create a system of inequalities where the last inequality is basically describing a case when we underflow. And in case of this system is unsatisfiable, then we cannot underflow. And similarly, we can create a set of inequalities when the last inequality describes the case when we overflow this buffer. And in case this inequality is unsatisfiable, this system of inequalities is unsatisfiable, that means that we cannot overflow. So in case both of them are insatisfiable, we proved this piece of code correct in a sense that there are no overflows or underflows. So I wanted to show you how we can do that, how we can solve a system of inequalities using a Fourier-Motzkin elimination. This might be an illuminating example, and the reason why I use Fourier-Motzkin elimination because this is the easiest to explain. There are other ways to solve these problems, and I will not talk about those because those are more complex, and yeah, so this is a good overview, and we use something slightly different in MSVC. Okay, so let's see if I can stop this. So this is the original set of inequalities from the previous slide, and I've written down, and this is what we will work with. So I will do some normalization. I wanted to have less than and greater than operators, not less than or equals and greater than or equals operators, not strictly less than and greater than. So what I did, I transformed the last inequality. So instead of strictly less than 0, I wrote less than or equal to -1. So this is equivalent than the original inequality. Next, I will rewrite these inequalities in terms of x. So this is just rearranging them. So let's focus on the rewritten inequalities, and let's see if we can infer something useful. So basically, if we look at the expressions in the rounded boxes, those need to be less than x, and the other two expressions need to be greater or equal to x. So let's flip some of the inequalities to see how they look. And then let's rearrange them. So now what happened, everything is on the left-hand side is less than or equal to than everything on the right-hand side. So so we only have a solution for this system if everything on the left-hand side is less than or equal to than everything on the right-hand side, and this is regardless of x. So if we get rid of x, I can still know when there is a solution to this system, so I can still know whether it is satisfiable or not. So basically, I can create a new system of inequalities that is equivalent to the previous set of inequalities, but it has one fewer variables. So this is basically the previous one. I just took all of the combinations from the less than side and the right and the greater than side and put them together. So now I can do the usual simplifications, rewriting the inequalities in terms of y. And now something interesting happened. So basically, I have a trivially false part of this system. So there is an expression 1 is less than 0. And this is obviously false. And because we have no solution to this system, and this system is equivalent to the first system we started with, this means that the original system is unsatisfiable, so there cannot be any underflow in the original code. And this is how we proved, at least partially, this piece of code correct. And let's see what would have happened if we didn't have this contradiction. So we could continue with the same process that I did before. We had expressions that need to be smaller and expressions that need to be larger. So we can use the same method to get rid of y, and basically we could get a list of inequalities that only consist of constants. And so this is why this method always terminates, regardless of whether the end result is satisfiable or unsatisfiable. So this is a great algorithm that was available from really early on for like centuries. The problem with this algorithm is that the number of inequalities that we need to solve can explode if we have a lot of variables. And also, this is a method that is reasoning about integers. And when we are programming, we rarely deal with integers. We have bit vectors. So we have a data structure basically that can overflow and have other interesting properties. And this Fourier-Motzkin elimination will not account for those possibilities. And also, we might have other values in our programs like floating points and so on. So this is not a silver bullet, but it can solve, it can be a useful tool if you want to implement something relatively quickly. So I wanted to talk about a bit more about these linear constraints, because one would think that having linear constraints is very limiting. But in fact, there are a lot of there are a lot of expressions that can be expressed as linear constraints. For example, if we have a nonlinear term like b times b, we can represent b times b with a new variable and reason about that in our linear solver. And the other thing I wanted to talk about is canonicalization. So basically, if we have a system of linear inequalities, every inequality can be expressed in this way, where x1, x2, and so on are unknown values, a1, a2, and so on are coefficients, and c is a constant. So I wanted to show you how we can normalize to any inequality, linear inequality, to this representation, because this can be really useful when we implement something like a solver, because then we can use one canonical form and reason about one canonical form rather than work with a diverse set of expressions. So for example, if I have something of the form x greater or equal to c, then I can multiply the inequality by -1, and then I have a less than or equal to expression. If I have an equality, basically I can express the equality with two inequalities, and then I can transform one of the inequalities into the less than or equal form. And if I have a comparison between two variables, I can subtract one of the variables and get back to the canonical form. And similarly to the method that I already showed you earlier, if I have a strictly less than in the source code or in one of the expressions, I can just add 1 to one of the sides, and this way I can get back to the canonical form. So there are many other ways to solve a system of constraints, and one way to do that is to use a theorem prover that has a large set of theories built into it, and it is usually very powerful. The problem is those powerful tools are usually much slower than the quick and dirty methods like the one I showed you earlier. For example, when I replaced our own in-house built solver with Z3, the test suite we had, the runtime of the test suite increased from 17 minutes to almost 3 hours. And this is something that we would not be able to ship to our customers, because you might imagine that analyzing the whole of Windows could already take days. If we introduce Z3 into, so it might not take days at the moment. It depends on what kind of environment do we have. But basically, if we would include Z3, it would definitely take days or even weeks to complete the analysis. And that would be bad, because by the time we have the results, the code would have changed so much, maybe it is no longer relevant to even look at those results. So let's see what can we do to leverage these theorem provers. So what we can do, instead of replacing the constraint solver that we have with a theorem prover, we can run the analysis as usual. And instead of reporting all of the warnings to the users, we can cross-check the facts that we have only for the warnings we would report. And this could help us eliminate some of the false positives without using too many queries with the theorem prover. So this is a method that we are looking into. This is often called refutation. So we are using a fast method to find bugs, and then we use a slower method to refute some of those bugs and only report bugs that are more likely to be true positives. So finally, I wanted to show you an example. When can path-sensitive analysis go wrong? So here is a code snippet, and in this code snippet, I would like to find a null pointer reference. So I run the static analyzer in MSVC on this code, and I will get an error. And if I look at this error closely, something might be suspicious, because this is a false positive. So when we have a path-sensitive error report, we often have some data that could help us figure out what was going on. In this case, we have a list of lines, and this list of lines will help us reconstruct how the analyzer came to the conclusion. And if we look at this list of lines, we see that we took the branch in line 11 and executed line 12. So we set the value of P to null pointer, and then we took the branch at line 15 and hit the dereference at line 16. So basically, the analyzer thinks that it is possible to take both of the branches, but if we look at the condition of the branch, we only take the first branch when x is negative, and we only take the second branch when x is positive. Of course, the same value cannot be positive and negative at the same time. So this is a false positive. And the reason why we have this false positive, because we are doing a local analysis, so we are analyzing one function at a time, and we have no idea what is positive is doing. When will it return true? When will it return false? So what we can do in this case, we can use annotations to describe how isPositive is behaving. So we can use an annotation to describe that. It will return true when x was positive, and it will return false if x is 0 or negative. Yeah, there is a typo in the slide. So basically, using these annotations, we can tell the analyzer what isPositive is doing, and after rerunning the analysis on this code snippet, I will no longer get this false positive because the analyzer will figure out that these conditions are correlated and they cannot be both true at the same time. So this is a great way to, so this is a contrived example. This is a contrived example because it is easier to explain, but often what we found, the number of annotations that we need to add to get rid of false positives is very small compared to the size of the implementation of the function. And one of the nice points about having these annotations is that they are like documentation. They tell the user how the function behaves, and this documentation is in some sense checked by the compiler, because if I get this annotation wrong, I will end up getting false positives. So it is almost like compiler check documentation. Of course, the syntax might not be nice. It might not be portable. We would like to make this more portable and nicer with contracts or some other language features. Unfortunately, at this point, we don't have contracts in the language. And also, the tools we work with, they need to support both C and C++, so we need a solution that works in both languages. Fortunately, there is a hope. There is a hope for attributes to be accepted into the C language as well, and there is a hope to eventually also get contracts in both languages. Question?
As specified, your when clauses are not exhaustive. They don't specify what happens when x equals 0. Does the rest of the system just tolerate that?
Yes, so the question is, so because of the typo in my slide, I forget to specify what happens when x is 0. Originally, the intention was for the second line to x smaller or equal to 0. I missed that. So the question is, whether our system tolerates that when these cases are not exhaustive, and the answer is yes. So we don't give any warnings to the users. So the user might not need to document, so the user might not need to add all of the annotations, and the reason for that, because we want the users to be able to add annotations incrementally, so we don't want to force them to add all of the annotations to all of the code base at the same run, because that would take a lot of time. So this way the user can add just as much annotation as possible to get rid of the false positives and get the more precise analysis for other warnings for free in some sense. So this can help to opt into these annotations incrementally. Okay, so I would like to summarize some of the lessons learned in this talk. So path-sensitive analysis is really powerful, but it comes at a cost. Usually, this cost materializes in runtime and also memory consumption. But it is more precise, and it can also give error messages that are easier to understand. Unfortunately, currently, we are not doing the best possible job to surface all the reasoning the analyzer has for a warning, but we are planning to improve this situation and ship features that will make it easier to understand why the analyzer thinks that there is a problem in the code. So in the future, expect to have nicer error messages from these tools. We are also actively looking into ways to make the analysis more precise. This includes both better language modeling and also better methods to solve the constraints that we collect along each of the execution paths. And there are large amount of checks that are already available in MSVC that you can use today. And we also plan to add more. And the reason why it is a really great news to have more checks in a path-sensitive framework, because whenever we add a new check that models a new part of the language, all of the rest of the system will get better. For example, if we add a check that reasons about optionals or null pointers, that information can be used to reason about, to get rid of invisible paths. For example, after modeling optionals, the analyzer would know that if I have a null optional and I convert that optional to bool, that will be evaluated to false. So it can use that to prune the branch when it would be true. And also, if we use some annotations to make our intents more explicit, it can greatly help the analysis to get rid of false positives. And it can also help us to improve the readability of the code base, because if we have a big function with a very complicated implementation, then those annotations can help us understand what sort of guarantees do I have for the return values of that function, and also what sort of preconditions does that function have that I need to satisfy before I call that function. So that is everything I wanted to talk about. So enjoy the rest of the conference, and there is a reminder for the Discord channel and the survey. And in case you enjoyed this talk, there are a couple more about the tools we are working on. So at this point, probably you can look at the recordings when they are released. So thank you for the attention, and if you have any questions, probably this is the best time to ask them. Yeah.
Question.
Mm-hmm.
When you put the attributes onto the function, are the attributes checked?
What do you mean by, so the question was, when I put attributes on the function, are the attributes checked? So what do you mean by checked?
Does the system trust the programmer, or does it check that those are true?
Okay, so the question is, does the system trust the programmer, or so I think the gist of the question is, do we look at the implementation of isPositive in that case, and would we warn if isPositive would do something different that would contradict the annotation?
Do you get an error if you got those wrong?
Yeah, so the answer is it depends on the annotation. For certain annotations, we do that. We do verify the implementation of the function, and we will warn when the function body is doing something different. But in this case, in this specific case, I think we might not get a warning, but I will need to double check that. So there is no guarantee to find all of the wrong annotations, but I think for most of them we will be able to catch when the implementation contradicts the annotation. Thank you. Other questions?
You mentioned at the beginning of the talk that the number of paths will dramatically increase with the number of branches in the room. So you said that you won't be able to check all functions for those reasons. You said you just want to check the interesting paths. How can you elaborate on that? How do you determine what the interesting paths are?
Mm-hmm. So the question was that since we have a potentially unbounded number of paths and we only want to check interesting subset of those paths, how do we determine which paths are interesting and which paths are not? And there are many different heuristics to try to guide the analysis. So one of the more important heuristics that we want to check as much of the source code as possible. So, for example, if we have a loop, we could try to model the paths when we have one iteration, the path with 2 iterations, the path with 3 iterations, and so on. And we could do this for a very long time. Instead of doing that and rechecking the body of the loop over and over again, we only have a very limited number of checks that we do with the loop body and then continue with the code after the loop. So basically, these heuristics make sure that we are not stuck into one particular part of the program, but we also reach to other program points. And optimally, we want to visit every program points at least once. There are many other possible heuristics. For example, if you are looking for one specific issue, not a wide range of issues, for example, you are looking for null pointer dereferences, you could guide the analysis to the paths that has dereference operations. And there is also a branch called concolic execution. So basically, one of the big problems with static analysis is the invisible paths. But the idea is that if you have a way to harvest paths at runtime, so you have a trace for a runtime path, you can guide the analysis at compile time, static analysis time, to follow that path, and that way you are guaranteed to evaluate only paths that can happen at runtime that are not feasible. Okay, it looks like we are out of questions, so thank you again, and enjoy the rest of the conference.